So trusses are used a fair amount to support load. They're kind of a way of spreading load out. Almost think of the load like a fluid running through the members of the truss. So instead of having a big solid beam, you often create a truss. They're lighter and you can kind of focus them to support the loads that need to be supported, okay? Just a little bit more efficient way of bearing load. So they're used in roofs quite a bit. You see them other places. You used to see them in bridges quite a bit too. And you see a lot of applications for these. That's just a simple greenhouse here on campus with a truss. So a truss is these long, thin members joined by pin joints into triangular panels. The loads are assumed to be applied at the joints. Because of the design on the members, the force, there are two force members is the term for that. That has to do with the two things that are happening there. The fact that they're supported by what we assume to be frictionless pin joints, which again is another one of those assumptions we make. Maybe not a perfect assumption, but quite often a good enough one for what we're doing. Okay. And also that the loads are applied only at the joints. Now all a truss can do then is support an axial force that goes from pin to pin. So that means a truss is either in tension or compression, one or the other, and the angle of the force equals the angle of the member in the truss. So when we want to figure out a truss, what we're doing is we're working our way through the members of the truss and finding the forces in the members. Okay, that's what we're doing. What we were working on last time was the method of joints, where we work our way from joint to joint through the truss and find the forces. Okay. Now, if you're going to do this, the first step is to find the angles for the members of the truss. That involves trigonometry, usually inverse tangents is what you do. Okay. All right. The next step is to find the reactions on the truss. You treat the truss as a whole thing, one object. So your free body diagram is the truss. And then you just take a moment about A in this case, and some of Fx and some of Fy. You find these reactions here. That one, and that one, and that one. Okay? So you need to do that first. You need to find the angles of the members, and you need to find the reactions. Okay? Now, once you've done that, you want to develop a strategy to work your way through the truss. So you start at a joint. A joint is where two members come together and are joined by a pin. You want to find a joint with no more than two unknowns and a known force that you can work with. So the places you could start on this truss are either A or F. Okay. I picked F, and when I did that, I could just start summing forces in the different directions to solve for the forces in the truss members. Okay. So I draw up a free body diagram of this joint, like so, and then I just start to work through that truss. So I can go, and where I start then is when I draw that up, I've got FDF, horizontal, I'm assuming it acts to the right. FEF follows the line of the member, so that's down at 56.3 degrees. I'm assuming that acts down and to the right, and then I've got the reaction. So I've got enough to work with. Okay. Then I want to get a strategy going here. Sum of Fx is 0, has two unknowns, DF and EF, so I don't want to start with that. I'll start with sum of Fy is 0, with one unknown. So I got 12,000 up, sine of 56.31 times FEF down. That allows me to solve for FEF. It's a positive answer, 14,422. The positive answer means my assumption of direction was correct. It does go down and to the right. That means it's pushing on the joint and it's in compression. Okay. Once I know that, I can go sum of Fx equals 0. I got FDF to the right, and I have EF to the right also, so it's cosine 56.31 times FEF, which I know to be 14,422. When I solve that out for df, I get a negative answer. What that means is it doesn't act to the right as I assumed. It acts to the left. If it acts to the left, it's in tension, it's pulling. Okay. Once I've found those, I can write them right on the truss with the arrows that show what they do to the joints over here, and then I can move on to another joint. And I just work my way through the truss. That's the basics of it right there. So do we got any questions on that so far? You just want to develop a strategy to work through the truss. You can either go to joint E or D, but D has 1, 2, 3, 4 unknowns. That's too many, but E only has 2 unknowns. So I could go to joint E. Okay, I have the sketch with the forces in EF and DF. I go up to joint E, and I just repeat the process. Okay. I find the forces at joint E, and then I'm ready to go to move again. I look at joint D, and I still have 3 unknowns. That's too many, so I'm going to go to joint C. And we'll get into something a little different on this one. Okay. So let's head over to joint C, and there's a free body diagram of joint C right there. So we're on page 490 and 500, that's where we're at. All right, now when I get to that joint, I can go sum of fx and set it equal to 0, and that'll get me FBC, which I'm assuming acts to the right, minus the 14,133, which I had found for CE. So that's easy enough. FBC is 14,133 to the right at joint C. That means it's compression. Now when I go sum of Fy equals 0, what do I got? I got FCD. Do I got anything else? Not really. There's no other members coming into that, nor are there any forces. So what that means is FCD is equal to 0. FCD is what's called, there's a word for it, well, not a word, but a phrase, zero force member. That's the term for that. It has no force in it. Okay. Now you might wonder, what's it doing there then? What's the purpose? Okay, now there's a few possible answers to that. 2 common ones. The first one is this is one loading for the truss, but there might be other loadings. We just might be happening to analyze this one where CD is unloaded, but there could be a different loading on the truss in which it is loaded. So that could be why it's there. Another common reason is not only do you have a bridge, if this is a larger bridge, in its final condition, but you have to build it. Okay, so sometimes when bridges are built, they start here with a pier and there with a pier, and they start to construct the bridge, and it has to support itself as they work their way out. I've seen some bridges built in that fashion. So that might be there as a construction member to hold it together as they're building it. Okay. It could be there just for aesthetics, so the bridge looks balanced. There's a lot of reasons why it might be there, okay? But just be aware that sometimes you can have members that have no force in them. They're called zero force members. That's not, it's fairly common when you're working through these, okay? So don't be fazed by that. Now also notice that you won't see that at D. There are so many things going on at D, you can't really identify CD as being 0 there, okay? But you can see it pretty clearly at C. So if you prove it's 0 at C, you know it's 0 at D. Okay, you just have to prove it at one joint. And quite commonly with these, you could easily see it at one joint, not see it very easily at all at the other. So don't be thrown by that either. If I prove it's 0 by analyzing joint C, it's 0. That's all I got to worry about, okay? All right. So are we doing all right with that? All right. How about drawing up a free body diagram of joint D there? You might need to make a couple assumptions, but that's all right. Don't, just assume one direction or the other for those forces. So you've got the joint there and put the forces on there. Remember, the forces follow the lines of the members. You've got the angles that we calculated there earlier. So just get the forces acting on that thing, okay? And you're going to guess at their directions. You're going to have to guess, for AE, you might guess right, you might guess left. I mean, it's okay either way. If you guess wrong, you just get a negative answer, and there's no harm in that. Remember the 9,000 down below. Okay. And you're just turning those members into forces. DF is in tension, it's pulling, so it acts to the right. Okay. CD you don't need to show because it's 0, so you can just eliminate it. It's like it's not even there. So to make this into a free body diagram is a fairly straightforward process. You just turn the lines into arrows, put an arrowhead on them one direction or the other, and you don't hang up too much on that. It doesn't really matter. I make my best guess, but if I'm wrong, it's not going to cause me any harm. And I put the angles in there. You okay? What I've done there is I've essentially cut this joint out of the truss. We talk about using a boundary on a free body diagram. There's my boundary, okay? Now let's solve it out. Which equation would you start with to solve this thing out? I think so. Why would you start with y? Yeah. One unknown. That's it. Yeah. Okay. So sum of fy is 0, and then off you go. Okay. So why don't you just get that one figured out? What's BD? And what all you've got there is a bunch of vectors. That's how I think about those. Those are force vectors just radiating out from D, and just write up an equation for them. And you've only got one that's unknown, so you should be able to solve for it. This is like those equilibrium problems we did when we did point equilibrium early on in the class. It's the same thing. We're just doing vectors and sum of fy. Should have 3 terms. little bit of trig on that. 9,000 will be negative because it's down. And then the signs of the angles, I think, because they're going up. The opposite sides are the signs, right? You got the angles, so what you're finding are the vertical components, which are opposite the angle. So those are both signs, like that, right? All right. Doing all right? Something like that. Sum of Fy is 0. Sine of the angle, 36.87 times the 7,667. That's this component right here, which we're basically, it's easier to see it for the right triangle over on that side, right here, basically. That's where you see it on the triangle, but you transfer it to D is what you do. You put it at D, apply it at D. And then we've got the other one as well, this side. Okay. So we've got sine 36.877667 positive plus sine 36.87 FBD positive minus 9,000. Run through the calculations, you get FBD is 7,333 tension because it's pulling. Okay, if you got time, do a sum of FX, and once you've got it, that'd be the next step. We got any questions on this bit here? Okay, so the next bit would be sum of FX. And that's going to be the cosines this time because the x's are the adjacents. Get that one and that one. So 1, 2, I think there's, how many terms? 4 terms in that one, right? 2 cosines and 2 just straight numbers, or two of them based on cosines. The 8,000 to the right, which would be positive, and the FAD to the left, which will be negative. Okay. Okay. Something like that. So minus FAD minus cosine 36.877333 plus cosine 36.877667 plus 8,000. So FAD is 8267 tension. All right, get you some of these to do for Wednesday. I think, are we good with that? Any questions on that? Now these things, they take a little while, okay? So 281 is one more equilibrium problem, then 292 and 294. These are due Wednesday. So list your answers in the order shown. You don't have to solve them in the order shown, but list your answers in the order shown. On what page that is, I think it's page 17. And draw a free body diagram of each joint. Okay, there we go. So those are due Wednesday, which would be the 26th, I think. Okay, So hope you all have a good weekend.